Everybody's here? Yeah, let's suppose everybody's here. Okay, so the first talk of this session is tightening leakage resilience of the suffix kit sponge. Is presented by Hank Branson and Bart Mannings. Yeah, please give your talk.
Yes, thank you for the introduction. So I'll start by explaining some concepts I will use during the talk. So first off, the suffix key sponge, which I from here on out will abbreviate as the SUX. So the SUX is a MAC function based on the sponge hash function. And just like the sponge hash function, it has a B-bit state consisting of an R-bit outer part up there and a C-bit inner part. And also it starts with an absorption phase where the plain text is split into blocks of R bits and XORed into the outer part of the state. And after each XOR, the permutation P is evaluated on the state. After the absorption phase, the function G is used to blend the key into the state. Then the permutation is evaluated on the state one more time. And finally, some inner bits of the state are truncated, and the remaining T bits form the tag T. The SUX is also used for authentication in the authenticated encryption scheme ISAP, which was one of the finalists of the NIST lightweight cryptography competition. And the security of the SUX has been formally analyzed by Dobrownik and Manning. And in their analysis, they considered an adversary who exploits multi-collisions. So that's multiple set of plain texts which collide on some state of the SUX. So for example, on tag. And to give an upper bound on the size of the largest multi-collision an adversary can find, they used something called the multi-collision limit function, which was formalized by Dahmen et al. Using a balls and bins experiment. So the definition is as follows. There are Q balls which are thrown into 2 to the power R bins according to a uniform distribution with replacement. And then the multi-collision limit function denoted mu of Q, R, and C is the smallest number x, such that the probability that the fullest bin contains more than x balls is at most x over 2 to the power C. So now I'll give an example to illustrate this definition. So we set in the example Q equal to 4, so we get 4 bins, and we set R equal to 2, so that we get 4 balls. And then the balls are thrown uniformly with replacement into the bins. So for example, like this. And then we get as fullest bin containing 2 balls. So the multi-collision limit function can be used to give an upper bound on the fullest bin. And this upper bound is only exceeded with a probability that depends on the parameter C. So now we get back to the SUX and the security bounds for them. So Dobrownik and Manning gave a security bound in the black box security model, which you can see on the slide. It consists of 3 terms, and you see also in some of them the multi-collision limit function, which we saw on the previous slide. And they've also proven that this bound is tight, which means that for each term in the bound, there exists an attack that matches the complexity of this term. They have also given a bound on the security of the SUX in the leakage resilience security model, but they have not investigated whether this bound is tight. So in our work, we investigated the tightness of the leakage resilience security bound. And specifically in this presentation, I will focus on the tightness of the third term in the bound, which is highlighted in red. And as you can see, it's also very similar to the third term of the black box bound. The only difference is the minus lambda in the denominator. And this symbol lambda captures the leakage. So before I go into the tightness analysis, I will first explain the leakage model we use, which is non-adaptive leakage resilience. So in this model, we assume that leakage is incurred by every primitive evaluation, and that the leakage is modeled as a function of the input and output of the primitive. The leakage function is non-adaptive, which means that it does not change. And the leakage is also bounded. So per primitive evaluation, there's at most lambda bits of leakage. So now if we apply this leakage model to the SUX, you get the picture you see on the slide. You see that each primitive, so the permutation P and the function G, leaks lambda bits. But in the case of the SUX, because the key is only blended into the state after the absorption phase, we can the state in the absorption phase is public, so we can ignore the leakage from that. And as for the function G, we assume that it's strongly protected, which means that it does not leak. So we can also ignore the leakage from G. And we end up having only leakage from the final permutation. So now let's take a look at the tightness of the leakage resilience security bound, and then in this presentation, specifically the third term. So recall, as I said, that the black box and leakage resilience bounds had very similar third terms. The only difference was the lambda. And to analyze the tightness of the term in the leakage resilience bound, we need to find out if there exists an attack that matches the complexity of this term. But because we know that the black box bound is already tight, we know that there exists a matching attack for this term. So we can use that attack as sort of a baseline to find an attack for this term. So now we'll first look at the black box attack. And we assume that the attacker can make Q construction queries to the SUX construction. So in the black box attack, the goal of the attacker is to recover a state W, so that's the state of the SUX here at the end, for one specific construction query. So the attacker already knows the first T bits, which are the tag, and has to guess the remaining B minus T bits. So if the attacker makes n guesses, the success probability is n over 2 to the power B minus T. But the attacker can also exploit multi-collisions. So if the attacker finds, say, mu queries, which all result in the same tag, then for one guess for the B minus T bits, the attacker can match each of these mu states W. So then the success probability is multiplied by mu. And now we can use the multi-collision limit function to give an upper bound on mu. So the multi-collision limit function which is used in this scenario is mu of 2q, t, and b minus t. And then if we plug that into the success probability, then we get exactly the black box bound. So that means that the black box bound is indeed tight. And the reason that we have the parameters of the multi-collision limit function like this, I will now go over now. So first, the parameter t indicates that there are 2 to the power t bins. So basically each bin represents an individual tag value, since it's also 2 to the power t tag values because the tag is t bits long. Then the parameters t and b minus t together sum to the state size b, which is usually the case when the multi-collision limit function is used in sponge constructions. And finally, there are 2 Q balls, and each ball basically represents a different construction query. But then the factor 2 is needed because in this scenario, the balls are not thrown uniformly with replacement, as is the case in the definition of the multi-collision limit function. But the distribution is very close to this. So then we use the result by Dauman et al., which states that for a close to uniform distribution D, the fullest bin in the balls and bins experiment where Q balls are thrown according to distribution D is at most as full as the fullest bin where in the balls and bins experiment where 2 Q balls are thrown uniformly with replacement. So now let's see how we can augment this black box attack with leakage to find out if it matches the leakage bound. So in the black box attack, the attacker's goal was to recover the truncated part of the state W. So we can use a leakage function that leaks exactly a part of this state. So for example, the leakage function you see on the slide leaks the first lambda bits of the state W after the tag. So intuitively, now the attacker just learns a longer tag than before. So now let's see if the black box attack with this leakage function matches the bound. So you see now the bound here on the slide. And as you can see, the only difference was the minus lambda. And this minus lambda appears because the attacker now learns a longer tag. So there's fewer bits to guess and hence less possibilities. But the problem is that the attacker still only has a multi-collision on the t-bit tag. So the attacker with one guess for these b minus t minus lambda bits cannot match each state W in the multi-collision. So the complexity of the tag is actually higher than the complexity of the bound, and therefore the bound is not tight. But for this specific leakage function, we can easily tighten the bound because we can just replace the multi-collision limit function such that now it also collides on the leaked bits. And then the attacker can match with each gets all the elements in the multi-collision. And this result also holds for any other leakage function which just leaks bits of W in a fixed position. But we do not yet know how to tighten the bound for other types of leakage. So now we'll take a look at one other type of leakage, which is called Hamming weight leakage. So the Hamming weight is simply the amount of ones in a bit string. And then with Hamming weight leakage, instead of leaking bits in a state directly, we leak the Hamming weight of these bits. And the reason why we chose Hamming weight leakage is first because it's a more realistic model than the fixed position leakage we saw before. Because in practice, Hamming weight can be used to model power consumption. And there's also 2 reasons that make it more interesting. So first, whereas with fixed position leakage, the entropy loss resulting from the leakage was always lambda, since the attacker just learned lambda bits from the state. Now the entropy loss depends on the leakage value. So for example, if the attacker learns the Hamming weight 0, the attacker knows that all the bits were 0 bits, then the attacker knows the whole value. But if the attacker learns Hamming weight 1, then the attacker knows that there's exactly one non-zero bit, but the attacker does not know where this non-zero bit was. So the attacker then learns less information than with Hamming weight 0. And also the Hamming weight leakage function is non-uniformly distributed because there's simply more values with Hamming weight 1 than with Hamming weight 0. So the Hamming weight 1 is more probable to occur. And so because of these last two reasons, it's also harder to analyze jointly the multi-collisions and the leakage together. So now the leakage, the multi-collision size depends on the leakage value, because for more frequent Hamming weights, the attacker on average can find larger multi-collisions. But also it's not no longer the case that the largest multi-collision is also the best, because it may be better for the attacker to use a multi-collision that collides on the leakage value, which results in a larger entropy loss. So now the multi-collision limit function must take into account the non-uniform nature of the Hamming weight, but also the value of the actual Hamming weight leakage. So we get the Hamming weight a multi-collision limit function for each possible leakage value. And this way we can sort of compare the different leakage values and see which multi-collision has the best balance of the entropy loss and the size of the multi-collision. So now we're going to take a look how to incorporate Hamming weight leakage into the multi-collision limit function. So the attacker's goal is still to guess the truncated part of W, and the attacker still knows the first t bits forming the tag. But now the attacker also learns the Hamming weight W of n unknown bits of the state. So now we're going to incorporate the Hamming weight leakage directly into the balls and bins problem. So we consider a bin for each possible combination of tag and leakage value. So as you can see, there are 2 to the power t tags multiplied by n plus 1 Hamming weight values, since the Hamming weight of n bits are leaked, and then the Hamming weight ranges from 0 to n. And then the balls are thrown according to a distribution we call the Hamming weight distribution. So this takes into account that some Hamming weights are more frequent than others. And also it takes as parameter a specific leakage value. So for example, the Hamming weight distribution of 0, it only counts the bins corresponding to Hamming weight 0. And the Hamming weight distribution of n only counts the bins corresponding to Hamming weight n. And we can use this to create a separate multi-collision limit function for each leakage value and compare them. So with this balls and bins problem, we get the following multi-collision limit function. So as you can see, the Q balls are thrown according to the Hamming weight distribution. And then there are 2 to the power t prime bins for a value t prime, such that we get exactly the amount of bins we need in the balls and bins experiment. So now we have a multi-collision limit function incorporating Hamming weight leakage. But the problem is that it's hard to compute because the balls are thrown non-uniformly into the bins. We can solve this by bounding the multi-collision limit function by another multi-collision limit function, where the balls are thrown uniformly with replacement, but there are more balls. So as you may recall, this is similar to what Daum et al. Have shown. They show that for a close to uniform distribution D, 2 Q balls were sufficient to do this bounding. But in our case, the distribution is too far from uniform. So we could not use this result directly, but instead we used the same proof strategy to arrive at a similar result. And that's that in our case, to bound the multi-collision limit function incorporating Hamming weight leakage, alpha W Q balls were enough. And the proof to bound this alpha W was quite involved. So I won't go into details in the presentation. But the intuition is that the alpha W results in a larger value for more frequent Hamming weights, because for more frequent Hamming weights, the attacker can on average find larger multi-collisions. So now let's take a look how to tighten the bound for Hamming weight leakage. So here on the slide, you see the tightened bound, which is quite different from the fixed position leakage bound, but I'll go over the changes one by one. So first, the denominator. So the attacker now knows the tag and the Hamming weight of n unknown bits. And we get that there are n choose W times 2 to the power b minus t minus n possibilities. So the n choose W term is needed because for the attacker, for the values for which the Hamming weight, the bits for which the attacker knows the Hamming weight, there are n choose W values because intuitively there for Hamming weight W, there are n choose W ways to choose the W bits that are set to 1. And for the remaining b minus t minus n bits, the attacker does not have any information. So the attacker still has to try all 2 to the power b minus t minus n possibilities. Then the multi-collision limit function has changed to incorporate Hamming weight leakage. And finally, the term max W has appeared in front of the bound. And this is needed to find this balance between the size of the multi-collision and the entropy loss resulting from the leakage value. because we consider an adversary that will exploit like the worst case leakage value. So now we've seen tightened bounds for both fixed position leakage and Hamming weight leakage. And now we're going to compare them to the original leakage resilience security bound in a SUX instantiation used in the authenticated encryption scheme ISAP. So in ISAP, there are multiple parameter sets for the SUX, depending on what permutation is used within it. But we have used the SCOMP parameters you see here on the slide. We also had to bound the amount of leakage. So we set lambda equal to 3 for the sake of example. And then in the case of Hamming weight leakage, we also had to bound the amount of bits for which the attacker learns the Hamming weight. So we chose n equals 7 so that there are 8 Hamming weight values, which fit exactly into 3 bits of leakage. So now on the slide, you see the bounds in the order of the original leakage resilience security bound, the fixed position leakage bound, and the Hamming weight leakage bound. And I've highlighted the third terms of the bounds, which the presentation focuses on in red. And then for the security, we see that both our tightened bounds improve the security, but improvement is smaller for Hamming weight leakage, which we believe is the case because the bounding of the alpha W may be lossy. So now to conclude, we have investigated the tightness of the SUX leakage resilience security bound and shown that it's not tight. Then for two types of leakage, namely fixed position leakage and Hamming weight leakage, we have given a tightened bound, which can improve the security. And finally, although we focused on the SUX in the paper, the multi-collision limit function is also used in other schemes. So our analysis of this function incorporating Hamming weight leakage can also carry over to these other schemes. And then as for future work, we believe it would be interesting to consider adaptive leakage, where the leakage function is allowed to change. And also, because we restricted ourselves to leakage of bits in fixed positions, it would also be interesting to look at leakage functions that leak bits in positions depending on the input of the leakage function. And that concludes my talk. Thank you for your attention.
Thank you for the talk, Hank. So is there any question to him? So if there is no question, I actually have one question to you. So I just wonder, the future work considering like additive case or dynamic positions, but can we also consider some another distribution of leakage, but for some fixed leakage, and then generalize your result for some arbitrary distribution?
Oh yes, yes, it would also be possible to, instead of considering a specific leakage function, to consider, well, just generic leakage, which is done as in the original bound. But we do believe that would be harder because it's just easier to work with one distribution than, well, generalizing over all of them. But yes, I think it would be possible.
Yeah, thank you. So this is the last chance. Okay, so thank you again. Okay, so the next talk is about constructing, committing, and leakage resilience authenticated encryption, presented by Maximilian Weichpalt and Patrick Stroke.
Okay, so thank you for the introduction. So as the title of our paper suggests, our goal was to construct authenticated encryption that is both committing and leakage resilient. And I want to start by talking about why these are security notions you should be interested in, both separately but also in conjunction. So let's start by looking at the following situation. So Alice and Bob are using some AE scheme to communicate with each other, and there's an adversary that wants to recover the key that they use. The adversary has access to a key dictionary that could stem from some leaked password data. So in the partitioning oracle attack, the adversary splits this set into two and computes a ciphertext as well as nonce and associated data such that they decrypt validly under each key from the first set, but under none of the keys from the second set. And the adversary then sends the ciphertext to Alice and depending on her reaction can draw a conclusion about the secret key. So in this example, the key K8 that Alice and Bob use is not in the first set, so Alice would not be able to decrypt. So in the original partitioning Oracle attack, Alice is a password encrypted server that answers automatically. So here she would return a decryption error. But then the adversary can eliminate all keys from the first set and continue this process with the second set. And this allows an exponential speed up compared to a brute force dictionary attack. So this attack, as well as the Facebook message ranking and the subscribe with Google attack, exploit the fact that there can be ciphertexts that decrypt validly under more than one key. And committing security was defined as a reaction to this, and to prevent such attacks, it has ciphertexts be commitments to a key. So staying in this situation, let's assume that Alice and Bob are now using this AE scheme on some embedded devices like their smartphones. Then our adversary could also conduct a side channel analysis, for example, exploiting the power consumption of the devices to extract secret information about the key, or in the worst case, recover it completely. So on the right, I list some papers that deploy such attacks against practical schemes, for example, ESCAN. So of course, we do not want such attacks to be possible, and to formalize security against them, the notion of leakage resilient AE schemes was introduced. So in summary, committing security and leakage resilience have gained a lot of attention recently, but they've only ever been analyzed separately. However, as we've seen, depending on the use case, it might be very sensible to consider them in conjunction. And in general, achieving multiple of these advanced security notions is beneficial, as it allows to shield against different types of attacks. So for this work, our goal was to find a way to construct authenticated encryption that has both properties. And in the following, I will explain which approaches we've tried for that and if they worked out. But before we do this, I want to give short definitions for our two main notions, starting with committing security. So the notion can be traced back to so-called robustness, which was originally only defined for PKEs, but then evolved over time. And we consider the committing notions from Bilal and Tong from 2022, which are CMT1, 3, and 4, for the latter two being equivalent. And also there's more development, as recently there have been two works on more fine-grained notions. So the committing notions are defined over the following security games. So CMT1, the weaker notion, here the adversary has to find two tuples consisting of key, nonce, associated data, and message, such that the keys are different, but both encrypt to the same ciphertext. And similarly for CMT4, the tuples provided by the adversary have to differ in at least one input, so not necessarily the key, but again, encrypt to the same ciphertext. And we focus for this work on the strongest version, so CMT4 security. And for sake of simplicity, we simply denote it by CMT in the following. Then for our second notion, leakage resilience, we follow the model from Barwell et al., and thereby also the assumption that only computation leaks information. So for LAE security, as for standard AE security, the adversary has to distinguish the real and the ideal world. So more precisely differentiate real encryption from an oracle that returns random values, and real decryption from an oracle that rejects all decryption queries, so always returns bot. But additionally to that, the adversary can obtain side channel leakage. And this is modeled by adding two leakage oracles, one for encryption and one for decryption. And for both, the adversary can query some input X and a leakage function L from some predetermined set of leakage functions, and as an output obtains Y, which is then either the N or decryption of his inputs, and the leakage function evaluated in the key and the inputs. So in summary, the adversary gets access to these 4 oracles. So note that to prevent some trivial attacks, some types of queries are not allowed. And then the adversary has to decide if these queries were answered by the real or the ideal challenge oracles. Okay, so as a first approach for our goal of committing and leakage resilient authenticated encryption, we consider generic composition, as it is a well-known and somewhat classical way to construct AE schemes. And here the main idea is to combine a symmetric encryption scheme and a message authentication code to form an AE scheme. And we consider the N schemes, which are based on the classical modes, but are designed concretely for non-spaced authenticated encryption with associated data. And they look as follows. So for N1, which follows encrypt and MAC, both ciphertext and tag are computed using the message. First, so for one as input to the symmetric encryption scheme and the MAC respectively. Then N2 following encrypt then MAC first encrypts the message, and the resulting ciphertext is then input into the MAC, which yields the tag. However, in both cases, both ciphertext and tag are output separately. And this is different for N3, which follows MAC then encrypt. Here the tag is first computed using the message, and then both message and tag are encrypted, and the symmetric encryption scheme outputs the ciphertext. So for the N schemes, they have already been analyzed with respect to their leakage resilience, with the result that only N2 can achieve LAE security. And the problem for N1 and N3 is that for both the ciphertext, an adversary can obtain decryption leakage even for invalid ciphertexts, because in both cases, the ciphertext needs to be decrypted before it can be validated. And for committing security, this analysis was still open. And in the following, I present our results for N1 and N2. And for N3, we neither have a proof nor an attack, so this is still an open question. Okay, so for N2 schemes, we show that committing security is not given. And we do this by providing a simple attack that needs only the assumption that we have a tidy symmetric encryption scheme. And the adversary then looks as follows. So firstly, he randomly samples some encryption key, nonce and message, and encrypts them to a ciphertext C. Secondly, another different encryption key is sampled and used to decrypt the ciphertext C, which guarantees that the resulting message will re-encrypt to C again. But then it is also easy to achieve same tags for this composition mode. As the ciphertexts already agree, we can just choose the same MAC key and the same associated data. And the adversary then wins the committing game by outputting these tuples we've just constructed. Okay, secondly, for N1, we show that committing security can be achieved. And we do this by proving the following theorem, which states that that if the symmetric encryption scheme and the MAC fulfill certain collision resistance properties we introduce, then also the composed N1 scheme is committing secure. And for the symmetric encryption scheme, we call this property weak collision resistance. And in the corresponding security game, the adversary is asked to output two tuples with different keys, but same nonce and message, such that both encrypt to the same ciphertext. And for the MAC, we just need a standard form of collision resistance. So with such a result, it's natural to ask if there are any schemes that fulfill these notions. And in our paper, we prove that for the sponge-based scheme SLAY, so the underlying components of it, this is the case. Okay, then coming back to our goal of achieving both committing security and leakage resilience, we have gathered the following results for the generic composition approach. So Barwell et al. Already showed that only N2 can achieve leakage resilience, and we have only positive result for N1, as we give an attack for N2 and have N3 as an open question. However, this already shows that one cannot achieve both notions simultaneously from generic composition. And this is why, as a second approach, we consider generic transformations. So there's already a number of existing transformations that achieve committing security. However, as far as we are aware, there are only 2 that achieve the strongest form, which is the one we consider in our paper, so CMT security. The first one is given as the composition of the HTE and the UTC transform from Bella and Hong. And here UTC transforms an arbitrary AE scheme into one that is CMT1 secure, and HTE upgrades CMT1 to CMT security. And the second one is the CTX transform from Chan and Roggaway. Okay, then without going into detail about these transforms, we see that in the BH22 transform, the key is fed into some hash function. And so if this hash function leaks, an adversary might be able to recover the key. And the same is true for the CTX transform, which also directly hashes the key. So in both cases, we would need a leakage resilient hash function. And to circumvent this, we propose a new transform that does achieve committing security and leakage resilience but without this requirement. And we call it the UTC star transform as it is an adaptation from the transforms from Bella and Hong. So it uses a hash function H and a keyed function F, and applied to an arbitrary AE scheme, the encryption works as follows. So first, nonce and associated data are hashed, and the result X is together with the key input into F, which for one outputs a session key K prime, which is then together with nonce associated data and message encrypted using the AE scheme. And secondly, F outputs a so-called commitment P, which is then returned alongside the ciphertext and tag. So the main difference to prior transforms is that the key is not hashed, but instead input into this function F, which then of course has to be leakage resilient, but we can achieve this using sponges by reducing the rate to a minimum. And while such a change would also be possible for sponge-based hash functions, where it seems really inefficient, as the hashing of long inputs would then be impractical. However, due to our change, all inputs to the hash function are public, so we are not dependent on a leakage resilient hash function. Okay, we prove the following results regarding the security of the UTC star transform. So firstly, we show that UTC star transformed AE scheme is committing secure if, for one, the underlying hash function is collision resistant, and secondly, if the function F fulfills partial bindingness, which is a notion from Bella and Hong. And here, the adversary has to find 2 different key input pairs such that their evaluation under F partially agrees. So the first K bits agree. And here K is the so-called commitment length, which is practically the length of the value P from the slide before. And secondly, we show that a UTC star transformed AE scheme is LAE secure if the hash function is again collision resistant, if our AE scheme is secure. So note that we do not need leakage LAE security here, just standard AE security. And thirdly, we want F to be pseudo-random even if it leaks. And this is formalized by the notion LPRF, which is defined in the same manner as LAE security, in the sense that the adversary gets access to a challenge oracle that either outputs random values or the evaluation of F, but also gets access to a leakage oracle and then has to distinguish the real and the ideal world using his ability to generate leakage. Okay, so in conclusion, we've seen that our first approach using generic composition did not yield positive results. However, we achieve our goal of constructing AE schemes that are both leakage resilient and committing secure using the UTC star transform. So thank you for listening, and I'm happy to answer any questions.
Thank you, Maximilian, for the nice talk. So, okay.
Okay, so many instances of generic composition have a pseudo-random key generation. So you have a master key, and then you generate the encryption key and the MAC key independently from nonce or associated data. Would that allow to rescue encrypt and MAC?
You mean because the attack would then not be possible because we need different encryption keys? So I think, yes, maybe, but I would probably have to think more about it to be sure. But then, of course, the attack is not possible as we do it now. So.
Yes, thank you. And then, is there any question? Yep.
So thank you for the talk. And I wonder the standards AEAD security of the new construction. Because if we look at the security bounds of your new construction, so the standard AE security advantage is multiplied by Q. So I think there is a security decrease here. And I wonder if you can prove what you can say about the standards AE security of the new construction.
Yeah, we have not thought about that yet. You mean if it has some advantage for the normal AE security?
Normal, if we can focus on the normal AE security, maybe you can prove, I don't know, stronger. It may inherit the original AE bounds, and you may have a stronger security bounds.
Yeah, I think we would have to look into that.
Okay, thank you.
Thank you. Maybe we have time for last one questions. Oh, actually, I also have a question. So I just wonder, your new proposed construction might not be an optimal, efficient one. So do you have any kind of intuition if one can make a like better efficient condition, better efficient construction which achieve the both security notion?
So what we have thought about is that the associated data does not need to be input into the AE scheme as well. So that might be a slight advantage, but next to this, we don't have any results on that yet.
Yeah, thank you. That may be an interesting future question. So thank you again. So this is actually the end of this session, but the next session will be immediately start. So the next session is about random generators.